This is the STEP Support Foundation module. This is assignment 4. It's about proofs and stuff like that. For the warm-up question, we have this triangle ABP, right? And once you draw it out, it looks something like this. We want to prove a circle theorem. So AOB, the angle AOB, is 2 times angle APB. Now, that's what it's asking us to show here, and we've got some conditions where APB is Q and AOB is less than or equal to 180 degrees. Now, there are a couple ways to do this question. The intended solution, which I saw, was what you do is you connect P together, and I'm sure if you've done GCSE maths, you'll know how to do this question because you do get asked for circular theorem proofs in GCSE maths, and I did do a question similar to this one, but exactly like this one, in a GCSE maths paper somewhere on the channel. So if you've seen that, then you'll definitely know how to do this. Now, what I thought to myself was, well, I didn't necessarily have to draw the triangle APB like this. I could have just drawn it. Oh, sorry. What sort of triangle is APO? APO is just where is it? A P. Oh yeah, sorry. I've like written the labels on like weirdly, but it's asking for this triangle here, and basically this triangle is isosceles because this OB and OA are just radii. Anyway, so what I was saying is, I didn't necessarily have to draw the triangle like this. I just chose to. Like, I'm allowed to decide how this triangle looks. There's no other restrictions other than this, and I can still meet these restrictions and change the triangle. So what if I brought P over here such that BOP was a straight line? So what if I did this? Right, this is still following the rules, right? And this is fine. And what I said was, well, if I call this angle here X, this AOB is isosceles, so this also equals X. And then this here will be 180 minus 2X. Now, POB is a diameter, which means that PAB must be 90 degrees. Okay, I'll get to that in a second. Anyways, angle APO must just equal 90 plus X, and then 180 degrees take away that. Right, so that equals 90 take away X. That's angle APO. Okay, now angle AOB is 180 minus 2X, right? And you can see that it's just 2 times it, right? So that's the first part done. Prove the same result where this triangle does not contain the center. So, it looks something like this maybe. Now, again, the solution that I went with is not the intended one. And to be fair, this is kind of cheating, I guess. I mean, it's not really. There's nothing that says I can't do this. But what I'm going to do is, also, let me just say, if you actually are doing this question for real, the best thing to do is to just join up things, as many things as possible, and then just start labeling angles and solving stuff. Anyway, so what I did was I just said, okay, well, let's just say we have another point up here, right? We'll just draw on these lines, and I'll call this angle here X, right? We've already proved that this angle AOB must be 2X. Okay, this is the point K, by the way. And I can say that AKB equals angle APB because angles subtended from the same arc are equal. That's just a circle theorem. So, yeah, that's the case, right? Which means that this equals X, right? And then you can clearly see that it's just 2 times the angle. So, that's that. Factorize this and then find the range of values with this inequality. This is X minus 4, X plus 1. Equals y, and it's greater than 0. So we have critical points when x equals 4, x equals minus 1, and we want to be greater than 0. So if you imagine just sketching the quadratic, then this is GCSE, you know how to do this, I hope. X is going to be greater than 4, x is less than minus 1. Also, it's that because it's a positive quadratic. Anyways, show that x equals 3 is a root of this equation here. So, that means that when you plug in x equals 3, you should get 0, because it intersects the y-axis, right? So yeah, just plug in 3 and then just go through it, you'll get 0, therefore it is a root. If you've not seen this symbol before, it just means therefore. Find 2 more integer roots and write this is a product of 3 linear factors. If a is a root, right, this is just factor theorem by the way, then x minus a is a factor, right? We have 3 is a root, which means that x minus 3 is a factor. And I couldn't just say that this polynomial here, this cubic, is just a linear factor multiplied by some other quadratic, right? Hopefully this makes sense, because then when you expand out, you'll get something x cubed and, you know, the rest of this. Now, if you just compare coefficients, right, you can see that when you expand this, you'll get ax cubed, but you know that a has to be equal to 1 because you're trying to get from here to here. So a must just equal 1. Similarly, you want a plus 6. The only way to get a constant term is to do minus 3c. So minus 3c must equal 6. That means c equals minus 2. And then for the b's here, you can look at the x squareds, or the x's if you want. But what we have is we have bx squared. So if I do this multiplied by this, and then what's the other way of getting an x squared? Well, I can do this multiplied by this. So I have bx squared, take away 3x squared, and that must equal minus 2x squared. All right, x squareds cancel on either side to 1, so you just get b equals 1. You can plug that in. This factorizes again into this, and then that tells us that we have roots. When y equals 0, x equals 3, x equals 1, and x equals minus 2, you can just draw that. It looks something like this. Obviously, the y-intercept is 6. You can just see here when x equals 0, this is clearly 6. It looks something like this. We want to be less than or equal to 0, which means that we want to be less than or equal to minus 2, or we want to be between 1 and 3. Factorize this, and then use your answer to help you factorize this. This is x minus 2x plus 1. But the only way to get a y squared, to get from here to here, is we must do y multiplied by y. Now, the only other case where you would do y multiplied by y, something like this, is if there was a y here and a y here. So this is x minus 2y multiplied by x minus 1y. You can just expand out and then, you know, just to confirm. And we're told that this equals 0. Okay, so you have critical points that x equals 2y and x equals y. You don't have to write this one. And then if you just change it around a little bit, you get y equals a half x or y equals x. Now, if you just plot that, right, so that's y equals x and y equals half x, you know, the gradient's just ever so slightly different. Then, you know, we want to be, is this an inequality? Why is the inequality? Oh, no, never mind, that's just it. And then it says that they meet at some point, I think, at the coordinate xy. The only point where these two actually meet is just at 0, 0. So the point is 0, 0. On a sketch, shade the regions of the xy plane in which this is less than or equal to 0. Now, when you factorize this, you get this, which we've just seen. And then we get these two lines, right? Now, the only way for this to be less than or equal to 0 is for one of them to be negative, for one of the factors to be negative, and then the other one to be positive, right? So let's just consider the case where this here is positive, right? And then that means this one here must be negative, right? So we're saying that this is positive, okay? And then that means that this x minus y must just be negative, right? This will get you x is greater than or equal to 2y, and then this will get you x is less than or equal to y. If you just think about this, how is x going to be greater than 2y but less than y, right? This doesn't make sense. There's no overlap. There's no overlap here, so therefore, you know, this can't be positive. This must be negative or 0, and then that means this one must be positive or 0, right? We must meet both conditions. So it's not this or this, it's this and this, which is what we want, which means that this here must be less than or equal to 0, and then this one must be greater than or equal to 0, so you get x is less than or equal to 2y, and then x is greater than or equal to y. It's an and, right? It's both of them that we want to meet. If you write them together, it looks something like this. This should have an equal sign here. I don't know why it doesn't. Anyways, we want to be basically, right, we've got this line here, so y equals a half x, and we want to be to the left of it, right? So the x coordinate is always going to be to the left of wherever the y coordinate is. So, you know, we're going to be on this left side of this line here, of this line. Okay, and then we're going to be to the right of the line y equals x, because x is always going to be greater than or equal to whatever the y coordinate is. So we're going to be between these two lines here and then between these two lines here, which is just this region. This is the step question. The last questions were preparations and warm-up. Find the real values of x for which this is greater than or equal to 0. Just plug in some random values. Try x equals 0, x equals 1, x equals minus 1. Just solutions that are very simple to just quickly check. Once you do that, once you plug in x equals minus 1, you realize that it is a solution because it will evaluate it to 0, which means that x plus 1 is a factor, and so we can just multiply it by some polynomial to get this back. A must just equal 1, right, because we've got a 1x cubed here, and then we want a plus 4 as a constant, so this c must just equal 4. Now, looking at x squared, right, we have this x multiplied by bx, so bx squared plus 1x squared, and that must equal minus 4x squared. So you get b equals -5 apparently. Okay, this factorizes more into this, and this is greater than or equal to 0. We've got roots at x equals -1, x equals 4, x equals 1, and then we've got a y-intercept of 4. I don't think I put the y-intercept, it doesn't really matter, I don't think they care. We want to be greater than or equal to 0, so we want to be between -1 and 1, or greater than 4, and that's it. Find the 3 lines in the xy plane on which this equals 0. You know, we're going to just do a similar trick to what we did last time. If this is this, right, and we want a y cubed, well, we can make a y cubed if this is y here, and then there's a y here, and then there's also a y here, right? So we'll just do that, and then we'll have roots that x equals -y, x equals 4y, and x equals y. And then if you just write out y equals, you know, you'll just quickly notice that this is just a line. Okay, I've changed this here to a greater than or equal to sign. I've drawn on some of the lines. I did not mean to, I meant to like put that in properly, you know, animate that in properly, but it's fine. This is going to be greater than or equal to 0 now, right? And so we want to find, just similar to the preparation question, you know, which region is actually shaded in. Okay, I'm not gonna, we want to be greater than or equal to 0. I'm not going to say that, well, this is positive, this is negative, and then this is positive, because two negatives make a positive, and then you'll have a positive, so this entire thing is positive. Or they're all positive, or maybe these two are negative, this is positive, or maybe these two are negative, and this is positive, because there's just, you know, there's just too many cases that I'll have to consider, so it'll just take too long. There are actually 3 choose 2, or 3 choose 1, same thing, cases that I'd have to consider, and that's just too long. I don't want to be wasting my time doing that. You could do it, you'd get the exact same answer, but what I'm going to do instead is something else, and I'll show you in just a second. What I'm going to do is I'm just going to do some test cases, and I'm just going to plug in values, coordinates from these different regions, and then just see which ones actually meet this condition up here, the initial condition. Okay, let's just try -2, 0. So that's within this region here, right? Let's plug in x equals -2 into here, and then y equals 0. So this goes away, this goes away, this goes away. When x equals -2, this is just -8, and we're saying that -8 is greater than or equal to 0. This is nonsense, so just ignore that. We're not in this region, right? That's what that tells us. Let's try maybe 0, 2, so maybe somewhere in this region up here, right? So we'll plug in x equals 0, y equals 2. This goes away, this goes away, this goes away. You'll have 2 cubed, which is 8. 8 times 4 is 32. 32 is greater than or equal to 0. That's fine, that makes sense, which means that we are in this region, so we can shade that part in. Another case, well, let's check 2 across and then 1. That gets us into this region, and if you're thinking to yourself, well, how do you know that it's not going to be below this line? What you can do is, you know that the line, the point 2, 2 exists on this line here, y equals x, because, you know, the y coordinates and the x coordinates just must be the same. So 2, 2 is somewhere on here. Maybe it's here, right? Okay, now if we just go a tiny bit lower, you know, just 1 unit lower, then that'll get us somewhere in between. And you can also just, you know, plug in 2, 1 into this one here, and then just verify that, you know, y lies above it. Okay. Anyways, yeah, plug in x equals 2, y equals 1. You know, it's a little bit of work, you know, just go through it slowly, make sure you don't make any mistakes. You'll get -6, right? We're saying that -6 is greater than or equal to 0, which is also nonsense, so just ignore that, but that means we're not in this region, right? Let's check another case, maybe 2, 0, which gets us this region up here, this down here, I mean. Okay, we'll plug in x equals 2, y equals 0, this goes away, this goes away, this goes away, this becomes 8. 8 is greater than or equal to 0. That is true, that makes sense, so that means we can shade that region in. This here, we can check 0, -1, which is this region here. When x is 0, this goes away, this goes away, this goes away. -1 cubed is -1, -1 multiplied by 4 is -4. It's not greater than or equal to 0, so this is also nonsense. Let's check this last region down here, right? I'm going to use a similar trick to what I did last time. I'm going to say that, I used actually a different one. So I said, let's maybe test this case, -2 and then -3/4, and I'll explain where that comes from. So we've got this line y equals 1/4 x, which is this one here, okay? Now, when x equals -2, right, y equals -1/2. So when we're -2 backwards, right, that means we're -1/2 down, or just a half down, actually, all right? Now, we want to be just a tiny bit further than a half down, right? And because as you go down, you're getting more negative. We want to be minus a half plus some small change. And let's just imagine that change is 0.25. So minus a half plus 0.25, that gets us somewhere here. And we can safely say that we are definitely within this region because the two coordinates are not the same, so they're definitely not on this line y equals x. So they're probably inside of this region, right? This is a little bit more work, to be honest. Just go through it carefully. It's not too much work. This is step, so you will have to do a lot of work. Eventually you'll get that this is greater than or equal to 0. I can't remember what it was. Maybe it's like 3 point something or 6 point something. It doesn't matter. What matters is that it's greater than or equal to 0, so it meets this condition, which means that we are in this region, so we can shade that in, and those are our 3 regions, right? So we considered this region, this region, this region, this region, this region, and this region. So there's only 6 regions. Careful, these coordinate axes they're not regions, right? So you can just ignore them. Now for the 1-down questions, for I, we have 4 double-sided cards, right? And they've got numbers and letters on them. These are the letters and numbers. This person is saying that if there's an even number on one side of the card, then there must be a vowel on the other. And how do we check his claim? By only turning, by turning some number of cards, right? Now we don't actually have to turn too many cards. We only have to turn 2, right? They're saying that if it's even, then there must be a vowel. This doesn't mean that if it's a vowel, then it must be even, right? It's not, it's just the way that the question is worded. It means that if it's even, then the other side must be a vowel, right? But just because one side is a vowel doesn't mean that the other side is even, right? If you've had a look at Tamua papers, which is it's an admissions test that you take when you're trying to apply for a maths course at university. They've got notes on logic and stuff like this, and necessary and sufficient conditions, and how you can write them in if, then, or if and only if, or if only if, stuff like that. I'm sure you might have heard it before, but they have some really good notes on stuff like this, and I think that would help a lot. And maybe I'll leave a link to it if you want to check it out. Anyways, so if it's even, then there must be a vowel on the other side, and if it's a consonant, right, it must just follow that the other side must be odd, I think, right? That was just my reason. I think that's true. I checked the answer and I got it right, so I'm guessing those 2 statements that I made are correct. I think if I'm wrong, please correct me. Anyways, what I'm saying is, well, obviously we need to turn the 6, right? Because if we turn the 6 and it's a consonant, it means that this claim is just instantly false, right? So we turn the 6 and then we should get a vowel. If we don't get a vowel, they're false. If we do, they're true so far. Now, the other thing that we can turn based off this second statement that I made is the other consonant, Q. E is a vowel, so just leave that, right? We can't say that just because it's odd that it's a consonant. We can only say that because it's a consonant, then it's odd, right? It doesn't go both ways, right? Hopefully that makes sense. So if we turn the Q, right, we should have an odd number on the other side. And if we don't, if it's an even number, then I think we can say that this claim is false. So we turn the Q, should give an odd, right? And I think these are the only 2 cards that we need to turn. Part 2, there's 2 identical ropes, okay, and it takes an hour for one of them to bend completely. How do we time 45 minutes? Like, to be honest, I'm actually quite proud of myself because I did this question in literally like 1 minute. I feel like it's kind of those internet style questions that you see online, like you have a 5-litre bucket and a 3-litre bucket of water. How can you measure some specific amount of water or whatnot? So we have these 2 ropes, okay? Let's just say they're these 2, and they're non-uniform, we're told, right? And what that means is we can't just split it in half and then say that, oh well, it must take half an hour for this one, and then we can split it in half again, and then that'll be this quarter would be 15 minutes, and then put this one here and just time how long it takes for this fire to get in line with the second rope, and that would be 45 minutes. You can't do that because they're non-uniform, right? Okay, so how do we time 45 minutes? Well, we're told we have a lighter, right? And I'm just going to assume that we can use a lighter as many times as we want, okay? if we light the same rope twice, right? So what I mean is, if we light this rope on this side here, right, it'll take an hour to burn through. But if we light it on this side and on this side, right, it's the same rope, right? So if we're doubling the amount of fire, right, we're halving the time, right? It's a it's an inversely proportional relationship. Okay, so I'll just say that again. If we're doubling the amount of fire, we're halving the amount of time. So if we light this one and then light this one, both on the same side, it should take 30 minutes for the full thing to, burn. And say we light both ends of this rope here, right? So it'll burn for 30 minutes. If at the same time that we light both of these ends, we can also light this one. So we'll just assume that we can light all three ends at the same time, and we'll leave this one here just for now, right? Because we're just going to want this to be burning at its constant rate, whatever that is. Okay, it depends on the length of the rope, right? They're identical, so it's fine. So if I burn two ends of this one, right, it'll go half an hour through while this one's also burning at the same time as these ones. When this is burned at double the speed, and then this one's been burning, at a half of this speed, I guess, or just the normal speed. This will be halfway done when this one's finished, right? And when it's halfway done, right, what we can do is we can burn. It's already burning on this side here, right? If you just imagine this has been cut, it's burning on this side. Now, if we light the other side, once this entire rope has finished, i.e., we've counted half an hour and this one's gone to half, we can light this half, right? So we have this half. Now we're going to double the speed, right? So that means, if we're doubling the speed, we're going to half the time, right? And we've already done 30 minutes. So once we half the time, it's another 15 minutes. So it's 30 minutes plus this 15 minutes that this will take, right? Because the first 30 minutes won't be equal to the last 30 minutes because we've doubled the speed once this one has gone halfway through. So we have this 30 minutes plus this next 15 minutes because we've lighted both sides. And then that will give us 45 minutes. And that's the full assignment. Thank you for watching. I hope that made sense.